is a classroom. The difference between school and life is that, well, in school, you usually get the lesson first and the test after. In life, you get the test first and the lesson after. And tonight, in this classroom, there'll be no tests. But there will, hopefully, be some learning, some opportunities for us to explore stuff together. Now, stuff is kind of a nebulous word. It can mean everything and nothing at the same time. So to clarify, by stuff, we mean thought experiments. So thought experiments, well, they're concerned with questions, like all sorts of questions. And they're also concerned with possible consequences and implications for those things. Now, each of the thought experiments that we're going to explore tonight involve three things critical to scientific and philosophical thinking: imagination, curiosity, and courage. So the first two probably seem kind of obvious, right? One of my favorite authors, Lauren Isley, once wrote that jumping into the unknown is only possible by great leaps of the imagination. Leaps that stem from and result in curiosity and wonder and awe. But what about courage? Why would a scientist or philosopher need courage? Well, because they're concerned with reason. And following reason where reason guides, well, that's something Plato said. Technically something Socrates said in Plato's works, because for all that we know, Socrates actually wrote nothing. What we know about Socrates came through Plato's works. He was a student of Socrates. Anyway, following reason where reason guides, that's not an easy task, because sometimes we have to give up all sorts of beliefs along the way, things that we've held really tightly to for a good portion of our life. What we're going to be exploring tonight starts with questions. The thought experiments that we'll be diving into are some of these things that weren't just minor shifts in the way that we understand the world. They were revolutionary. We're going to be starting with Copernicus and Galileo, moving into Newton, and then Einstein. Now, of course, there's all sorts of thinkers and other thought experiments we could add to the list, but, well, frankly, time, if time exists, we kind of limits us for this evening. Now, to help us navigate these fun tides are two of my favorite thinkers and lovers of philosophy and science. First, we have Michael Chapman, who is going to play our philosopher extraordinaire for the evening. And then we have Martin Richard, who, for those of you who know him quite fittingly, would be playing the mad scientist. Now, neither Martin nor Michael hold themselves up to be experts of philosophy and science. However, they both do know a lot about both. They've dedicated a long portion, and I'm giving them a jab right now because they're old, long portion of their life, to studying and doing science and philosophy, and to better understanding themselves and the world around them. Now, I'm Marisa, or I guess that's what my name tag says, so it must be true. I'm Marisa, and I'm the student for the evening. And I'm here with my backpack and my notebook, and in this classroom with all of you, eager to learn.
Michael, why are we here?
I can't imagine.
That brings up one of my favorite things.
Oh, but you would.
Well, imagination. One of the things when I talk about science that I try to get across to people, and it's very difficult, is how science requires imagination. People think of science as just numbers, reciting facts, and they go into school sometimes and they're required simply to memorize facts. Okay, and they don't see the acts of imagination that science requires.
Well, you at last have hit on something that we both agree on.
Oh, I thought this was the right room for an argument.
Oh gosh, I'm sorry.
Okay, well, all right.
Well, okay, I left my boxing gloves.
Well, but science and imagination, I think, go hand in hand.
Yes.
Maybe, strangely enough, not to appreciate science or to learn science, but to do science requires imagination.
Especially if you want to design an experiment, and then you do a thought experiment first.
Well,
Every time
by thought experiment?
Well, think of it this way. Every time you make a prediction of anything, like to take a step, that is preceded by thought. Thought always precedes action. And that's as true when you're trying to design an experiment as it is getting up in the morning, taking a shower, going to work, coming home, fixing dinner, and going to bed. Now, that's all habit.
Well, my
So
dinners
it's-
are often experiments, yes.
I lose my way often enough, yeah. But the point being that the predictions that you make then are turned into motor activities through motor cortex, and then you actually do them.
Okay,
But what I'm trying to say is, doing a thought experiment, for instance, the people who had to imagine the physics of the Manhattan Project, none of them had to deal with radioactive material and die because of it, at that point anyway, because they could think through it. They had the knowledge in the background of how these things worked. They could picture, that is, imagine, the way the pile would work as they got it all together. And as it turned out, they were spot on, which was a very good thing because we could have lost Chicago.
yes, well, there were some disadvantages. But I think that one of your discussions and our discussions, you keep coming back to the time of Copernicus, and you keep talking about that as a great earth-shattering thought experiment. Can you explain that a little?
Well, ultimately it was. It actually started slowly and dragged its way out over a century.
Okay.
But the point was, once the spark was lit, once the decision was made, once the culture decided that that was right, there was no turning back. And that's the same thing that we do individually.
I have a question. Where?
I'm a student.
Oh, okay.
Yes.
So I heard you talking about imagination.
Yes.
And I don't quite understand this world of Copernicus. Is there something we should be imagining that I'm not getting?
Yes.
Okay. We, in this age, we grow up, there's a lot of people. Okay. We grew up in this age, we knew that, we know that the earth spins. We know that the earth spins around, we know that we go around the sun does not go around earth.
Yes.
But at the time of Copernicus, I think there were some predecessors to Copernicus who understood that the sun was at the center, or rather the earth moved around the sun and not vice versa, right?
Yes, glad you brought that up.
Okay.
And in fact, there's a really basic part of science here. No scientific innovation does not depend on what has come before.
Right.
It's a stair-step kind of
Standing on the shoulders of
Yes.
giants.
Yes, precisely. That's an ancient metaphor. And it's as true here as there. Probably the first known person who made the connection was Pythagoras.
Really?
But he's not thought
He of the theorem?
Yes, the right theorem.
The right, okay.
And he thought that Earth orbited the sun.
Really?
Yes.
I knew about a couple of people, like
Aristarchus.
Aristarchus,
who came a couple of hundred years after.
I thought he was a dinosaur.
Oh yeah.
Okay, okay.
Aristarchosaurus.
Aristarchosaurus Rex, I think. Okay, so there were some people,
Yes.
a thread, an intellectual thread, but the common people, most people at the time of Copernicus believed that the Earth did not move
Yes.
and did not spin.
For one reason.
Why?
Aristotle.
Oh, okay.
He overshadowed everyone. And Aristarchus was actually punished for publishing that view, that
Really?
the heliocentric hypothesis. And Aristotle then took over the minds of Western civilization for about 2,500 years.
Okay, so as they say, took over the minds of Western civilization. Let's engage in your imagination for a second. Okay, what I would like to have you do is try to imagine yourself at the time of Copernicus. Try to imagine yourself as that you thought, you grew up knowing that the earth was solid, that the sun rose, that the sun moved around the earth, yeah, from that direction, yes. Okay, moved around the earth, and that the earth was the center of the universe. So I would like you to try to get back to that, to use your imagination to think that what that was and why, then try to imagine what it must have been like when they heard this, when they first learned the news, and how it must have been very difficult for them to believe this when all of their lives, they were on the solid earth.
Yes.
And now we learn that it's spinning. And people would argue, if it's spinning, why don't we fly off? There were a lot of arguments about it. Now we consider them settled, mainly because, well, first of all, because we can see pictures from outer space. We're pretty sure it's a sphere. The Earth is a sphere, okay? And so we now know this, but then they did not. So it will take you an act of imagination to go back to their time.
I'd like to add a thing to that. The fact was, that picture of the universe was not an option. I mean, it was the only game in town. It was the only acceptable picture, the world view. And in fact, it could be punished for denying it.
Right.
And plus,
Galileo, right?
Yeah, he was next on the docket. But the point being that the entire system of ethics, morality, interpretation of history, predictions into the future, all of them were based on the Earth standing still in the very center of the universe, and stationary. Is
this where we get into like talking about how what you learn in science has much wider implications?
Oh yes.
When we learn these things, but they're not isolated facts. They're how they shaped their universe. They're how we shape our universe. And again, sometimes it takes an act of imagination to get back to that. It
would be virtually impossible. We are free people. We are not under the thumb of a particular worldview that is keeping all of the political power, that has all of the authority over your life from death to birth. Death to birth. There's a neat idea. Reincarnation. Okay, that's the next one. Come back next week.
Yeah. Okay, come back next time. So Copernicus, again, shifted the worldview.
Yes.
They had to do that. What would be your next Earth shatter? My next one would be something like Galileo. I liked Galileo. Galileo was, of course, we all know that he was the first one to turn a telescope to the heavens. Okay, he was the first one to see the moons of Jupiter. Okay, and that was eventually earth-shattering too. And that required a great deal of shifting of the acts of imagination. But Galileo also did, this brings us to one of Galileo's thought experiments, which I just want to put just lay it out there for right now, because we're going to come back to it. Okay? Galileo had one of the very first thought experiments that I think is really an experiment of more what people mean. He asked you to imagine being on a ship, a sailing ship on smooth water, and the ship is enclosed. You can't see out the window. Okay? And he asked is a simple question. How can you tell you were moving? How do you know that you were moving? Now, he imagined it in a ship, in a sailing ship. We could imagine it in a train. Okay? And for example, Einstein used the train a lot. Didn't have too many rocket ships in his time. But I'm sure you've all had this experience of being in a train, and as it starts up, it moves so slowly, and you can't tell whether you're moving or the train next to you is moving. Okay? And we know that that's an illusion, but it's actually a deep, meaningful illusion. It points to the principle of relativity, of the principle of relativity of motion. And that little thought experiment from Galileo was eventually going to lead to Einstein.
Yes. I'd like to go back to Copernicus
for
a bit, because Galileo was one of the early believers, at least in a scientific sense, of the literal truth of the Copernican hypothesis.
Okay.
The important thing to realize is, really, those people 100 years before knew basically nothing of what Copernicus said, because when he first published, his books were read only by a few people.
Okay.
They were the ones who could digest the mathematics, because they were quite a bit more complicated than they had been before.
Right.
The important point was he established a work which was a seed that would grow into a mighty oak. and it took a long time for it to make that kind of penetration.
Okay.
So by the time, we're talking about 80 years from the time Copernicus died. And, you know, we talk about courage. Copernicus wasn't the most courageous of scientists. He waited until, he hung on to the book until he was literally on his deathbed. And then he said, okay, publish.
Right, and am I remembering this correctly? I seem to remember this anecdote. It was published, and he didn't literally publish it on his deathbed, but someone else wrote a preamble.
Yes.
Someone else wrote a preamble and said, oh, this is not real. This is not real. It's just a means of calculation. Okay? It's just a way of calculating the heavens, and it's not actually real. And that preamble was not written by Copernicus. No, but he didn't even publish because he was afraid.
Right.
Okay.
I can almost remember his name. Yesterday I remembered it. Right?
Yes, of course. Okay.
But,
I have a question.
Yes.
So, at least with Copernicus, why does it matter if we're not at the center of the universe?
that's a good student question.
Well, it matters a lot if you think that man is the end all, is the purpose of the universe. If you think that man is the purpose of the universe, then naturally you're going to put him in the center. If you're going to put him in the center, you're going to put everything revolving around him, which is exactly what they did. The Earth, everything revolves around man. That's, I think, approaching an answer. And so when you move man from the center of the universe, it's not only Earth, it's not literally earth shaking. It undercuts what you think of what they thought of at that time to be human. To be human.
To which I would add, it's perfectly logical to think, as we walk through life, we're the center of our perceptions. When we think of the world, we're still at the center of our perceptions. So now we try to build a picture of the world and the world in the universe, and it's perfectly logical. It is common sense that it is at the center. And to which I would add, my favorite saying in the world is this: common sense is the sense that tells you the earth is flat. We always hold common sense up as the final arbiter of value. We listen to a politician say, I'm going to do this because it's common sense. And I say, well, that almost proves that it's wrong, because there's a lot of common sense that should be uncommon. And so the common sense picture is that Earth is the center. We're the center of ourselves. We're a baby in the cradle is at the center of the family. And as you grow, then your perceptions are the center of your consciousness. And you just keep extrapolating like that until finally you get to this sphere, this fixed stars out there, as Aristotle saw them.
And this brings me to one of my main points, since I'm the guy in the lab coat. Okay,
what?
That part of what you need imagination, yes, but it's imagination constrained by data. Okay, because what finally broke open that was that worldview was, again, Galileo, and the data was pretty simple. Moons around Jupiter. Okay, here were things in the heavens that did not circle the Earth; they were circling Jupiter. Okay, and that that simple data point shattered. Was the opening crack that shattered that worldview.
And shattered Galileo in the end.
Yes. And Galileo was really not the first scientist, but he was really one of the first to do actual experiments. To try to construct, again, imagination and theory constrained by data. Okay?
Yes, importantly in a couple of points. One of them was Galileo was not a philosopher. In fact, he was adamantly not a philosopher. His hero was Archimedes, who was the world's best engineer in the ancient world. And he read Archimedes because some of the works of Archimedes had just been rescued in the fall of Constantinople. And so he was never indoctrinated as an Aristotelian. And to him, reading Copernicus's hypothesis was like listening to a song, bursting into song. And he could see immediately what was going on, but he couldn't prove it. Not until in 1612, when he designed and he built a telescope. Interestingly, he wasn't the first one to look at the skies.
Oh.
There were two boys in Amsterdam, and they had these lenses, and they discovered that if you had one weak lens and one strong lens, you could hold them like this and move them out, and it would magnify what you were seeing.
Okay.
Nobody had thought of that before. It came down to a child, once again.
A little child should lead.
Yes, whose imagination is unconstrained. But it was recorded by Huygens, I think.
Okay.
And Galileo heard about that, and Galileo from that designed a telescope,
Which he built.
and created the lenses. And his first one was only a 3 power, but finally got to a 36 power. And when he got to that power, he could really start to see details.
The
Yes, ma'am, wait a minute. Here she is.
Oh, I know. Okay.
She interrupts all the time.
I have questions.
Okay.
Okay.
So, Copernicus and Galileo were no longer at the center of the universe. We're kicked out.
Okay.
Okay, and that revolutionized science, and if I understand you correctly, also more than just science, right? It
Right,
changed-
Philosophy,
Okay.
worldview.
Right.
Who else? There was someone else that we were like, who's the next person that
Um,
just changed?
Glad you brought up that.
Oh, right. Oh, right. Here's a gimme. There you go. Yeah.
If we can leave Galileo behind, but understand that this next person we're going to talk about worshiped Galileo and referred to him often as the true father of modern science. And his name was Isaac Newton, a thoroughly reprehensible character.
Oh, he was a terrible person. Didn't want to be around him.
Sallow-faced, yes, didn't show up if he didn't want to. But he had one quality that didn't really endear him to anybody, but put him at loggerheads with others in the Royal Society, about which I want to make one quick note. Science has always depended on government support. And that goes as far back as science goes, all the way to Babylon. It is always done because it is an activity of the culture. There are individuals in it, and they do their experiments and so forth. But it is a cultural artifact, and a very, very important one. So here's Newton, who never would have come to anything if it hadn't been for the Royal Society,
Okay.
which had been created when he was 18 years old.
Okay.
By this time, he had discovered a great deal of things because he constantly thought about the environment around him. The way he put it when before he died was, he said, "I feel like a child who was walking along the beach and just picking up pretty stones." He says, that was my attitude toward life.
Can you help me imagine the world of Newton, since Newton's
Yes.
no longer alive, right?
Oh, that's easy.
Right?
He was the fig guy.
We're right here.
Yeah.
We asked you to move back to the time of Copernicus, because right now, you're in the time of Newton. That is to say, that's where you are most comfortable. You are very comfortable in what Newton did, what Newton set up, we now live in for most of our life. You had
Everything you see.
okay, Newton am I right? Newton was the first to synthesize something of the heavens. He recognized, the part of the story is the apple falling and whacking him on the head maybe, but he saw an apple falling and he was puzzling over the planetary orbits. Now, Copernicus and finally Kepler had worked out the orbits, but they didn't have a small little mathematical piece that explained it. And Newton came up with it and he sat on it for years, if I recall.
Oh, yeah.
And he did, and then somebody finally asked him, and he said, "Oh yeah, inverse square law."
Yeah, he did it 15 years before it really became an issue. And he was always working, and anybody who would see his office would see piles and piles and piles, but he knew where every one of them was. And when somebody came back to him, wasn't Bacon, doesn't matter, but who came back to him and said, "You've got to help me solve this problem." And he said, "Oh, I already did that."
Inverse
So I
square law.
reached down,
And that-
yep, yanked it out of the pile, showed him, yeah, it was all laid out. But Newton had shoved it aside because he said, if I'm right and the moon is orbiting Earth and that is the same force that is holding it in its orbit that that is happening when we drop an apple on the ground.
It's on the side.
Where I was?
Yes.
Yes. Oh, got it. Okay.
Yeah, we were going to drop the apple.
Okay, so Newton was
You
okay.
wrote it.
You go. Okay, go.
Okay, if I drop this apple, I did that on purpose. If I drop the apple, it drops straight to the ground. Aristotle said that's because it's natural motion. That's its natural place. And when you drop a stone or anything, it falls because it's heavy. And this was kind of the basis of a great deal of Aristotle's physics. Newton, well, actually Galileo undercut Newton's physics in several different ways, which I won't go back to because we probably don't have time. But in the case of Newton, here's the moon sweeping across the sky on a 28-day cycle. You know, we know that. Something is attracting the moon. And Kepler called it a hunger. He said, the Earth is hungry. And that was why the moon, he said, I know that's a metaphor, but that's the idea. Something I need, I've got to hold on to it. And the metaphor was very powerful. Well, Newton said, well, we know that things drop straight down if they are released. But if I throw it, you be ready back there? No. If we could throw it hard enough, let's say we go to the top of a mountain, and I'll put a cannon up there.
There's your cannon.
Oh, wow.
Well, okay.
Yes.
That's the best I can do. Okay.
Sure.
Okay.
Yeah. He said we put a cannon on a mountaintop and fire it.
Is this the thought experiment?
Yes.
This counts as a thought experiment.
Thank you for bringing that up.
Okay.
Yeah. This was Newton's thought.
This was an illustration from
He had
the.
already done the work that finally led to the famous equation G times m1 m2 over r squared, which is the universal law of gravitation. And it says that you have two bodies, you multiply their masses together, and then multiply them by the gravitational constant. That's the G in the equation, which is a very, very small number. And so the idea being that in this case we have a cannonball, and the cannonball is attracted straight down to the Earth, but because it has forward velocity, it also translates this way and finally hits the Earth down here. Interestingly, if you shoot the cannonball straight out at the exact same time you drop one to the Earth, they will both hit the Earth at exactly the same time. Because there are two different motions going on here. Here's one motion, here's the other motion, but this motion equals the motion all the way down here. So the point being, he was able to split those forces apart and recognize that they could be calculated by the use of the gravitational constant. Later on, he realized that holds the whole solar system together. All of the planets are held together exactly as the Earth is. Moon orbits the Earth.
Okay, yeah, and wasn't this his illustration of an orbit eventually?
Oh yeah, yeah.
If you keep firing the
Yes.
cannonball,
Yes.
keep firing the cannonball more and more powerfully,
Yeah.
it falls, and eventually it falls around the Earth.
Yeah.
If you fire fast
Exact
enough.
balance.
And we call that an orbit.
Yeah.
But basically, the cannonball is still falling. Everything that is in orbit around the Earth, everything that's in orbit around the Sun, is falling
Is being pulled down.
by the gravity.
That's what.
And so, but the great thing was that equation, G m1 m2 divided by r squared. Okay, that applies to everything.
And this is the R, the radius.
That applied, he said, universal law of gravitation. And that was Newton's great unification, where the same equation governs that apple as governs that cannonball, as governs the moon falling around the Earth.
So
Okay.
the same laws govern the planets
Yes.
and things on Earth.
Yes.
So why does that matter?
Well, the tides, for one, there's a good example. He was the one who made the connection between the moon and the sun and the tides. As it turns out, the sun is far enough away that it has about the same pull on the oceans that the moon does. So, if you, very quickly, the reason this matters is it's immensely important to shipping. Because the tides rise and the tides fall, and you have a tidal table, but it has to be corrected constantly because nobody can really tell why the water is pulled. Well, it turns out that formula solves that problem.
So math can be applied to anything.
That-
right.
Buildings, ships,
That's right.
tides.
It was called the Universal Law of Gravitation, again, because he applied it both to things on Earth and to things above. Okay? There was a great moment in, do you remember Apollo 13? Okay, not only the movie, but the when they lost power and they were coming back to the Earth, and someone says, well, who is guiding the ship? Who is guiding the spaceship? And the answer was Newton. Okay, at one point when they're coming back to the Earth, and there's no more, they have to do one final burn, and they have to make into the Earth's atmosphere within just a couple of degrees. Okay, have to be so precise. Come in too shallow, they burn up. Come in too shallow, they bounce off. Come in too steep, they burn up. Within a couple of degrees, and they had to do that extremely precisely, and all of that was governed by that equation. Who was driving that spaceship? Isaac Newton.
So does this matter outside of science?
Oh, did you catch that? I mean, yes, of course, it matters.
Philosophical.
For
Okay.
a million reasons. It's not first. This wasn't Newton's only equation. He's got several equations that literally have shaped the world, absolutely shaped the world, bar none. Far more than Copernicus as far as practical application. But the point of this one that makes it so important is this takes over from where we would have said in the past, like in Galileo's day, that Aristotelian physics said that anytime you have something moving, it rolls to a stop. And that means that that's the natural motion, and that's a given. And Galileo said, no, if we were outside the atmosphere, this is his thought experiment, brilliant thought experiment, because nobody had gone outside the atmosphere. But he said, up in space, outside the atmosphere, if I pushed a weight, it would go forever in a straight line, unless it was diverted by gravity. That was his insight. See, now that's his thought experiment that opened the world of physics to what Isaac Newton would then
But that's still
pick up and
science.
build.
So what about outside of that? Like,
Yes,
I
like
think about,
industry, like money, like actually it comes down to medicine.
Okay. Can I run with it for a second? Okay. One of the reasons and one of the important things about science to me is that it allows us to open up our appreciation of the much larger world. When a baby is born, an infant, you just brought him home to the hospital, the infant, that infant's world is the crib. That's his entire world. Okay? After a while, he expands his universe to include the room and the people in the room, in his bedroom. Okay? Then his universe, as he starts moving around, as he starts gaining motion, his world expands to the house. And eventually his world expands to include the school, etc. As your world expands. Okay? Part of the reason why I love science is because it allows me to continue that expansion of my world. Okay? To see that this applies, this is my world. And to understand more of it, this is where science comes in, and it's a constant expansion of our world. If you don't look at it, you occupy a very narrow universe. Okay? But the universe I try to occupy includes not only Earth, the solar system. We talk in our science class about the expansion of the universe. That is an amazing thing. That is a wonderful thing that we can do, and we cannot do that without science. We could not have done it without science. We could not have understood what a wide, wide world we live in. Yes?
Next question.
Sure.
So at least the first three we've talked about, Copernicus, Galileo, and Newton, seem to fall within the common sense intuition type stuff, and are at least expanding the
That's the
parameters of
Aristotelian
what
world.
common
That's
sense
what we think of
includes.
as the common sense world. Okay?
Is there anyone thought experiment-wise that did the complete opposite?
Just before we leave there, can I say one thing?
Sure.
You've made the point very clearly that it expands your world. Science expands your world.
Okay.
When people ask me what I like about science, I say it has given me the greatest aesthetic appreciation of the beauty of nature and the incredible web of life that we live in. What we're talking about now is dead stuff. I mean, according to Aristotle, the entire world was a living organism. Along comes Newton and says, no, it's a bunch of dead stuff. So, see those animals? You can slash them. That's okay. They don't feel anything. They're just robots. Newton demystified the world. Newton removed spirit from the world and left us imprisoned in steel and glass, which is where we are right now. And that is our barrier against nature. We have escaped a great part of nature. When's the last time you were exposed to natural selection? I say, take your clothes off and stand out in the parking lot.
In Chicago right now.
You will be exposed to natural selection. You won't like it. So, the point being that Newton really demystified the world and left us with a machine. And the machine paradigm has now absorbed the entire world around us and left us with no roots. Yes.
Okay. Clockwork Universe.
Not common sense.
The Newtonian universe, the Aristotelian universe, is often known as the Clockwork Universe, where we imagine it to be just be ticking along. Ticking along is very important, okay? Because Newton felt that time was absolute. That if you set a clock, if you have a clock here and you have a clock on Alpha Centauri, or you send a clock out in a spaceship like that, you set them, they will all be ticking at the same rate. He thought that time, that distance, the way you measured distance was always the same. That the way you measured time could be universal. That time just flowed and we flowed along with it. But along came a patent clerk, okay, who at the age of about 24, in 1905, changed that universe. And it started with a thought experiment when he was 16 years old. This was a guy by the name of, what's his name? Oh, yes, Einstein. Albert Einstein, at the age of 16, had this wonderful thought experiment. He said, what would happen if I could travel at the speed of light? How would I see light? That was his basic thing. If I could travel at the speed of light, how would I see light? And that puzzled him very deeply. And he resolved that puzzle about 8 years later, working as a patent clerk, okay? And he used two things. One, back to Galileo, the principle of relativity of motion. Here's a thought experiment for you. Imagine you were in a spaceship. Imagine there is nothing else in the universe, okay? You, the spaceship, are alone. Look out your window. Are you moving? How can you tell? You have nothing to measure your motion against. Now, imagine there's another spaceship. Now you have a universe with two spaceships. That you see that spaceship going by your window. You say, aha, another spaceship, it's going that way. But which one is actually moving? Which one is doing the moving? The guy in the other spaceship would say, aha, there's a spaceship going in that direction. You say, no, you're moving, you're going that direction, I'm staying still. He says, no, you're moving in that direction, I'm staying still. You're both right. The principle of relativity of motion. That is, if you are moving in a straight line, uniform velocity, not changing speed, not changing motion, then you cannot tell, then the laws of physics should be written so that they work for both spaceships. Both spaceships should be able to write an equation that works for whether or not this guy is moving or that guy moving. Both have the right to say, I am at rest, and you were moving by me. Take that. That's one principle, one idea, and add one more. The speed of light is always the same. Now, this came from Maxwell. Maxwell wrote down an equation, very famous set of equations, in which, for the first time, a velocity appeared. In this equation, which governs electricity and magnetism and all that stuff, c, the speed of light, it appears. And that equation is supposed to be universal for all people, even if they're in a spaceship, moving nearly at the speed of light.
This all seems spooky. What does this have to do with
The
our
reason it
world?
seems spooky, is because most of your life has been spent very, very far away from the speed of light. You are right now moving at a very small fraction of the speed of light, and you will never move anywhere near the actual speed of light.
7.5 times around the Earth in 1
What?
second.
Say it again?
7.5 times around the Earth in 1 second.
Correct. Speed of light.
Very good.
186,000 miles per second, 300,000 kilometers, 7.5 times around the Earth in 1 second. But the speed of light. Now, if you could do an experiment, you've got these two spaceships. If you could do an experiment with this one that measured the speed of light different than this one, then you could tell that one of you was moving. Okay? If you could tell that one of you is moving, you were violating the principle of the relativity of motion. If you start with that, no, each person has to say, I can say that I'm at rest, and you're moving. No, I'm at rest, you're moving. You got to write the equation so they're both right. Okay? And from that, and you got to write it such that the speed of light always comes out at 186,000 miles per second, or you're not using Maxwell's equations anymore. And that's the basic idea of relativity. Now, your question was?
Seems spooky.
Seems spooky. A few minutes ago, we asked you to imagine what it was like at the time of Copernicus, when everybody thought that the Earth was solid and the Earth did not move. What we're asking you to understand here is to, and you can think of the puzzlement of those people when they first started worrying that the Earth was actually spinning. Now, what we're asking you to recognize is that same puzzlement. That's what people feel when they start talking about relativity, when they start talking about time changing, when they start talking about that clocks change, the clocks go slower when you're moving toward the speed of light, from my point of view. If you are traveling off in a spaceship, and I see you from relativity, and you get close to the speed of light, your clock slows down when I look at it. But I'm back over here, and you look at my clock, and you see it slowing down, and you're both right. Yes. And that's hard to get your head around.
It's impossible to get your head around.
Well, I have a very large ego.
You can, well, yeah, it's one of the biggest things I've ever seen. But the point being, here I've drawn a graph, and I can give you a little idea. Let's say we'll look at things from Newton's view. There's an absolute scale of space from very small to very large, infinitely large, perhaps, and time from very slow, very small to very, 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 very high. Well, if we look at this, and note that this gives us a graph of all possible speeds. If you look at it, speed is equal to space over time, miles per hour. And centimeters per second if you're going to school these days. So if we just look at this graph, down here we have 0 space and 0 time. Up here we have the maximum possible speed, and that is the speed of light. All operations in the universe, according to Newton, would fall in somewhere in this square. But when you look at our zone, we call it the zone of middle dimensions. We're kind of sort of between the biggest and the smallest. Down here we have quantum stuff.
We're not getting there. We're not getting there.
I know. Pity that. That'll be next week also. And by the way, that was discovered by Einstein too, and one of his helpers. So between these two, at the speed of light up here and at absolute 0 and extremely small, we find this little tiny niche up here, and this is where all the visible universe exists.
This is where we inhabit.
Yeah,
We're not in the realm of the very small. We're not in the realm of the very fast. This is our comfort zone, yes.
So if we're not on spaceships passing one another, how do we know this actually works?
Well, okay, Einstein worked out those equations. They've been confirmed time and time again. And there's a really good experiment that was done that demonstrates that he was right, and it is called the atomic bomb. Okay? If none of this was right, atomic bombs would not work.
Wouldn't
Okay?
that be a tragedy?
Well, but it's real. And it is absolutely real. He showed in his second paper on relativity, the first paper was in 1905 on the electrodynamics of moving bodies. Notice relativity is not in that title. Okay, and then he wrote a second paper where he proved the probably the most famous equation of all time, E equals mc squared, where he showed that mass is just energy very tightly wound. Okay, that equation follows straight from the special theory of relativity, and that equation is what determines what happens when an atomic bomb blows up. That determines where the energy comes from. So, in one sense, it's part of our everyday life for anybody who is concerned about nuclear war.
How about if we don't go with the atomic bomb?
How
Is there another way?
Oh, Geiger counters. Well, nope, that's getting into quantum stuff.
Well, we could generate electricity.
I thought I heard something about phones.
What?
Phones.
Oh, no, okay.
That was phony.
All right. We're going to have to skip ahead for a second. But this is one of my favorite stories. Okay, we've been talking about the special theory of relativity. Special theory of relativity governs, is basically about whether things are going near the speed of light or very slow or near the speed of light. But it's only concerned with, remember I mentioned this, uniform motion. That is to say, two bodies or two people or two spaceships that are moving without acceleration, without changing paths, without like that. That's the special theory. That wasn't good enough for Einstein. He wanted his theory to encompass accelerated motion. Okay? And he wanted to expand from the special theory to the general theory. Special theory is, believe me, easy. The math is high school math. It just takes reading about it and absorbing it and reading about it before you finally accept it and get your head around it. But the general theory is much more difficult, and the math is way beyond me. Okay, the math, and it doesn't when general theory. When I first started reading about general theory when I was in high school, okay, and that was eons ago in 1960-ish. Okay. At that time, in 1960, the general theory, nobody studied it, except me. But nobody actually really worked with it not because the math was so hard, because there were only 3 experiments which touched the real world. One, general theory explained the orbit of Mercury. The orbit of Mercury shifts by a little bit, and that shift was explained by Einstein, not by Newton. Okay. The second one was the deflection of starlight. Sir Arthur Eddington did a spectacular experiment which he proved that as light travels by, the light from a distant star goes by the sun, it bends. And he caught that with an eclipse. In 1919, Arthur Eddington led 2 experiments, 2 things which measured the deflection of starlight, and overnight made Einstein famous. That was when Einstein became the first global celebrity, really. And certainly the first global scientific celebrity, except maybe Newton. But this was global. Okay? And that was the general theory. There was one more experiment which showed that in a gravitational field, time changes. We're talking about clocks flow differently when they speed, but actually clocks flow differently depending on the gravitational field. An atomic clock at that ceiling goes at a different time than an atomic clock on this floor. Okay? And it's measured. It can be measured. That was it. And so nobody really studied the general theory. And then they discovered pulsars. And then they discovered black holes. And now they needed the general theory to explain the energies that they were getting out of these creations, out of these things. Okay? So suddenly, everybody was studying the general theory. And the general theory was out there and was being used. So it went from 3 to another. Now, here comes the best part. GPS, the global satellite positioning system. When NASA first started putting up the first satellites for global science position, there was an argument between the scientists and the engineers. The scientists said, hey, look, you're above the atmosphere there. Your gravitational field, you're outside away distance in the gravitational field of the Earth, and you've got these atomic clocks essentially circling the Earth. You're going to have to account for the general theory, or your clocks are going to be off. You know, you're not going to do this. This is not going to work. The engineer said, nah, we don't do it. Silly scientists, we don't do general theory. Okay, we've never had to do general theory in our life. What are you talking about? And the scientist says, you better. And the engineer said, no. And the scientist said, you better. And then NASA finally said, okay, we'll draw the software both ways. We'll make the software work one way or the other, and we'll just flip it, depending on whether or not we get it to work. So they got it up. They got the general, and they, of course, discovered GPS doesn't work unless you accommodate the general theory. So, anybody got a smartphone in their pocket? Anybody ever use maps function on your GPS? You are using the general theory of relativity. Okay?
You are, yes. And that's a real, that leads us, how much time do we have left?
Our class is almost done. But I did want to ask a
Can we
question.
move slower and speed of light?
No, can we move faster?
Oh, no.
You're on the station.
But so we actually use the general theory every single time you pick up a smartphone and try to find where you are.
Okay.
Am I right to think from a philosophical standpoint that I can see now why that matters to our lives here, even if it doesn't, even if it seems spooky, it still has some effect here.
Right.
Philosophically, I'm thinking, and correct me if I'm wrong on this, that one of the reasons that this also matters is the idea that any invention that we come up with has the ability to be used for, like in the atomic bomb, good or bad. And
Right.
so that in some way, ethics are always to some degree built in to the things
Ethical
that we create.
questions.
Ethical
Right.
questions and ethics on some level are built into science
That's
and our
ethical
inventions. Is
concern,
that?
certainly so.
Right.
The one thing, I would like to say a couple things about that. If I can remember what I was just about to say. Notice what's happened over this discussion. We've gone from living on the planet, half naked, killing animals to get their skins and get food, to a culture that is big enough and now does agriculture, so now we have lots of food, and so we grow into empires because now we have lots of food, and so we have lots of babies, and then we want to kill the people next door because we want their land and their fields, and that's the history of the human race in brief, and out of briefs. But the point of it is that science, if we look at science about from Babylonian times, 3000 BC approximately onward, we see this steady progression of separations from nature. We've gone from actually being subject to natural selection to replacing natural selection with human selection. Darwin called it artificial selection. So now we're living in a, quote, safe environment, except for all the bad guys out there who are trying to blow them all up, a minor disturbance. But the point is, we've gotten farther and farther away from the common sense world that our brains evolved in. And we can learn, that's why we have education. But the fact is, by the time we get out here and we're saying, you know what, if these satellites go down, if China really has the code that allows them to turn off the GPS satellites, and I wouldn't be a bit surprised if they had it, I'm not paranoid because they're actually after us, you know, like that. But the fact is, the instant that happens, you're screwed. We're all screwed. We are totally dependent on this gadget technology that we have given ourselves over to, and which now have complete control over our lives. And it's very comfortable. We don't even think about that. I do think about that. That's why I'm so short. I figured I'll go high to close to the speed of light and get very heavy.
E equals Michael C squared. Tightly bound, right?
Okay.
So just to wrap that up, and then I'll drop it. That's dropping the bomb, I suppose. The fact is that when you ask, what does this mean to me? I can say, on one hand, it makes a correction that makes your GPS work. On the other hand, it makes you absolutely vulnerable because now we are placing our faith in this network of satellites outside the atmosphere that none of us can fix. We don't go up there with soldering guns and fix these things. And so we have to recognize that we're walking along the edge of a cliff and the path is getting narrower and narrower. And
so we have a great responsibility with the inventions that
yes.
create the imagination that we use
yes.
and the courage attached to it.
That's right.
To move forward or backward sometimes.
Yeah.
But there's also hope here.
Yes,
I
like hope.
It's the thing with that.
Little dark, Michael.
Okay, we started off one of my main themes with science that bothers me when people dismiss science, because people will look at science and think it's all numbers, it's all facts, but it requires a great human act of imagination. To actually do it requires imagination. So that's a human quality. It is constrained by data and by reason, and we have to be able to reason and to reason properly and to be able to reason well and understand what the numbers are telling us. Okay, but back to that other thing that I was talking about is when we grow up and when we expand our world, when we start off as babies in a very small world and grow into the larger one. We grow into that larger one by appreciating it through science, and that includes us all. Okay? That world, the world of the crib, the world of that small home, does not include anybody but that household. The world that we are talking about here is an expansion of humanity. It is all about, it is our shared humanity. Okay? I think it was Rubin, but I'm not sure who it was, but in the time of the Nazis, okay, there was a scientist, the scientist worked on science, and he said, science is what, at that time of that great persecution, he said, science is what kept us human. Okay? By doing science, they were expressing their humanity. Science kept us human. Science encompasses us all.
Yes.
Thus,
I have
Some philosopher takeaways.
yes, philosophy stuff.
Yeah.
And, well, one of them is, if you're not into science, it's really worth getting into science because of the beauty that it reveals. That is just a takeaway right there. But there's something that's more important.
I remember you said something about its relationship to our everyday lives, beyond just...
Yes, definitely. Well, and to me, that's the aesthetic part of it. And there's one other that's more important than that. And right now, unfortunately, ask me after.
Is it all that we see as our mistakes?
Oh, that's another one, but that's a good one. When we look back at the time of Copernicus and before, all we see is the errors of their reasoning and understanding, because they didn't have telescopes and so forth. And they had this little worldview. Well, now we feel like we're on top of it. Well, they felt they were on top of it. They thought they were right, just like we think we're right now. A century from now, if there's anybody left to check it out.
Again, going a little dark.
Oh, sorry. Yeah.
Happens with philosophy sometimes.
Yeah, well, that's true. It's called reality. When they look back on us, they'll probably think of us as infants playing with stones on the beach, just like, what's his name?
Newton.
What's his name? Now is his what's his name?
That's his first name. Isaac is Latin for what's his name.
And I guess I have some takeaways as a student, providing some. I think one would be, don't be afraid to ask questions. And Heather and I wrote them down so I wouldn't forget. Remain open to the wonder of the world. Embrace learning. Everything can teach us something if we actively engage in the process. Work hard. This is one of my favorites. Work hard to replace your exclamation marks with question marks. And when an exclamation mark seems warranted, at the very least, write it in pencil. be kind and open and humble. This speaks to a certain extent about us being in it together. We are all in this together, in this sort of grand experiment. I guess along that line too, being kind and open and humble, and would be grateful. So I want to say thank you to my partners in crime and friends, Michael and Martin. It's always great fun working with you. Thank you to Exploration Works for this wonderful opportunity. Thank you to HCTV. You guys have stood by us on so many things, so this will be recorded and put up on our website and available for your viewing pleasure. Thank you to Carroll College Philosophy and Engineering Department. They were kind enough to loan us this very handsome rolling board, which will be very fun rolling back to the campus tomorrow morning across the way. Thank you to Plato Philosophy Learning and Teaching Organization, and last but not least, thank you to all of you for taking the time out this evening and spending it with us. One plug, for those of you who have not seen Silent Sky playing at Grand Street Theater, very much in line with the wonder and imagination of philosophical thinking and scientific thinking, and seriously someone who revolutionized science. It was about Henry Leavitt's, plays through February 23rd. That's just a little love for that one. It's an awesome play, and it's so well written and acted. So that's that. And then Sarah, if you would like to come up and say us a few words.
I was just going to say a quick thank you. I'm the education director here at Exploration Works. Real quick question, how many of you have been to Exploration Works before?
Me.
Well, you're here every week. So it looks like a few people, this is your first time here at Exploration Works. So thank you for joining us tonight for the Science on Tap. I hope that we got your gears turning, your mind spinning a little bit, and asking those questions, which is the biggest piece in science, is ask those questions. Replace the exclamation points with question marks, because that's what it leads to, more and more questions. Also, I'm going to do a quick plug for Exploration Works. Our summer camps go live tomorrow. So if you happen to know somebody who is summer camp age, if you want them to continue to be curious, to come do some hands-on learning, not only that kind of big picture thinking, but digging deep into why. How do I manipulate this? How can I change my world? How do I make sense of all of this? We've got camps running all summer, all different topics. They're tons of fun. So, thank you again for coming tonight, joining us at Exploration Works. And I think we're gonna kind of do some mingling if you have some questions. I'm gonna head back in there if you'd like to grab another drink. Yeah. So, if you have any questions. Thank you.